Welcome to the webinar Incorporating Greater Than and Less Than Values in Data Analysis. My name is Dennis Helsel and I'm with practicalstats.com. This webinar is just one of a series of webinars that are related to our training course, Non-Detects and Data Analysis. And so you get a flavor for the types of things that you will be able to learn when you take that course. So again, this is a topic on censoring. That's what the statistics term is, where you have data that are below or above a threshold. That's what censoring means in statistics. And in this webinar, we're going to talk about what do you do when you have both less thans and greater thans in the same data set. So the objectives for today, to show you examples of what you can do, what methods are available for incorporating both less thans and greater thans into analyses. And we'll do that for computing summary statistics, hypothesis tests, and regression. I'll tell you what interval censoring is, because that's the process that's used in doing these procedures, is something called interval censoring. And that's how it's represented in the software, and would be how you would represent your data to the software, as giving it an interval of what the data values might be. And I'm using this to show you the major focus of my work for this year, because I'm working on interval censored methods. And there will be one or two scripts that you'll see here that are in progress and will be done. One of them fairly soon, and others by June at least. And so I'm just giving you a heads up on the types of things that you'll be able to do soon. If you want more information on some of this, and especially on the input of data to interval censored methods, and then there's some on the methods themselves, you can go to the book that I wrote back in 2012, Statistics for Censored Environmental Data using Minitab and R, and get some more information there as well. All right, so to put data into these procedures, you'll have to store them in a particular format, and this is called the interval endpoints format. It's the second format in that textbook that I just mentioned for censored data. And so the interval endpoints format is where you have two columns to represent a censored variable, and the first column is the lower limit, the low end of what the data values might be. And the second column is the upper end of what those data values might be. So for a less than 1, for example, you probably would have a 0 in the lower column and a 1 in the upper column. It's between 0 and 1, and that's what you know. A less than 5 would be between 0 and 5. A detected 10. Detected values get input by having the same number in both columns. And then what about greater thans on the upper end? Well, the lower limit would be that limit of 30 in this case, if it's greater than 30, and the upper end is a missing value. And that's pretty typical in software. The missing value is used to indicate going up to infinity. And so if it's greater than 30 and you don't know anything else other than that, it's from 30 up to infinity somewhere. Okay, so it's somewhere beyond 30, and that's what you know. If you do have an upper bound, you could put that upper bound in here and say it was from 30 to 100. But for most of the times that people have these greater than values, you don't have an upper bound. So in R, the missing value indicator are the letters NA, and if in a numerical column it sees letters NA, it treats that as a missing value. This kind of input will be used in R to represent the Y variable if you're doing regression, the variable that you're interested in if you're doing hypothesis tests, etc. We'll have this format. And when you put it in, you're going to designate that this is the format you have, and in R it's called the interval 2 format, the interval 2 option, I assume because of 2 columns. Looking at greater than values is not the primary use, or has not been in the past, for the interval endpoints format, for doing interval censoring. here's the primary use in environmental science for interval endpoints, and that is to represent differently data that are below a method detection limit and data that are below a quantitation limit, and especially data between a method detection limit and a quantitation limit. So if you had a method detection limit of 1 and a quantitation limit of 3, let me remind you what those things are. A method detection limit is a value that you cannot distinguish from 0. So if you have a less than 1 and it's the method detection limit, it's saying it's somewhere between 0 and 1, and 0 is a possible value for that. If you have a quantitation limit is the limit above which the lab is, I'd call it comfortable, but they have a reason why they are saying above that limit, they can give back to you a single value to represent what was in the sample. And so it's really an issue of signal to noise. And the noise is small enough related to the signal that they'll give you back an individual value, say of 5 or 10. Below the quantitation limit, the signal is small enough compared to the noise that it's really noisy. And so if they give you a value, so here is one down here that I've labeled 2J, and often a lab would give you a qualifier for that value of 2, either a J or an E or some other letter or an asterisk, or they have various ways. And sometimes those letters mean different things. But the usual meaning is that it's somewhere above the method detection limit, so it knows that whatever it is you're measuring is actually there and is not 0. But it's below the limit, in this case 3, for where they're comfortable giving you a single value. So it might be what they would tell you if you got on the phone and talked to them. We think it's a 2 plus or minus 0.5 or 0.8, something like that. And that's what the 2J is. What users often do is to drop off that J. And when you do that, you're saying more, you're lying in part way. You're saying more than what the lab has told you. For example, if you had a 1.5J and then a 1.8J, and you drop off the J's, you've just said that the 1.5 is lower than the 1.8. And even worse, with parametric methods, which are not just dealing with ordering ranks, but with parametric methods, you're saying you know that the 1.5 is 0.3 units below the 1.8. And neither of those things is true, that you know that. So it could be, if it's a 1.5 plus or minus 0.5, and a 1.8 plus or minus 0.5, that the 1.8J is actually lower in truth than the 1.5. So there's this noise that causes these qualifiers. One of the ways you can represent them is it's in the range between 1 and 3, between the method detection limit and the quantitation limit. So these interval sensor methods have been used in environmental science primarily for this purpose, but that's not what we're talking about today. But I thought I ought to let you know it's the real value for them. It's the use that I usually put them to, and the reason why I'm this year coding these things up in a way in R that you could use them easily. You don't have to work through all of the jargon for the primary applications that these were developed for, which is in medical statistics. And I'll show you a little bit of that jargon today, just to let you know why I'm doing it. All right, so the methods can be classed either in parametric methods or non-parametric methods. Down here, I've just giving you a little clip from the web page that says in November 2015 is that PDF file for statistics for doubly censored data. Again, doubly censored is having data that are both below a threshold and above a threshold in the same data set. So I do give you some more detail there, and you can download that directly off of your control panel. If you like to, you can go to the news archive and get that. And the difference between parametric methods and non-parametric methods, in parametric methods, you have to assume a distribution. You're going to give it a mathematical formula that the data you think follow. While Non-parametric methods are distribution-free. So we are going to look at very quickly maximum likelihood estimation for assuming a distribution, the parametric approach, and something called the Turnbull estimator for a non-parametric method. That's what you would use to estimate things like means, medians, etc. And score tests, which are based on the same kind of thing for doing testing. The data that I'm going to use in the webinar comes from the Ontario Pollen Monitoring Network, and they were concentrations of thiomethoxam, which is a neonic, which is a lot easier to say than neonicotinoids. I have to think about it before I say it. And the problem with those, you're probably familiar with by now, is that it kills indiscriminately with insects, including honeybees and other bees that we think are very beneficial. So it's something that is being regulated actively right now. So the data set came with 4 different groups. They were 4 stages of plant growth. And so we're going to do some group tests, something like analysis of variance as the parametric or Kruskal-Wallis test as the non-parametric, but adapted for censoring and adapted for double censoring. The original data set in these box plots are in these 4 groups. And you'll notice that in the second group that what's called the whisker for the box plot goes up and you don't get to the end of it. So I've changed the upper end because otherwise I couldn't see anything about the boxes. And there are 3 points above it in this group at 25, at 40, and at 80 way up here. So what I've done, I've left the 25 alone, but I have changed the 40 and the 80 to be greater than 30 in this data set to get a data set with greater thans. And so that's what I'm using throughout. And so I'd like to know if I could do things like doing a group test to see if their means or their medians or something are different in these groups. And then I've also created a new variable that to be a continuous variable. You might think of it, if it were available, I could have done it with time, and if that was meaningful to see if these things were changing over time. But what I did was just go in and put in the numbers 1, 2, 3, and 4 for the 4 groups. But at any rate, that gives me a continuous variable so that I can do something like regression. So that's what we're going to do. So the data set, here's a piece of it. The less than 0.05s go from NA to 0.05. You could put a 0 here. It actually doesn't matter whether it's an NA or 0 for any of the distributions that I normally use or for any of the non-parametric methods. The NA and 0 will be treated the same. But for the normal distribution, normal distributions can go negative. So if you don't put a 0 in here, you're going to have things that go down below 0. Part of the mass in computing the mean, it may be below 0, probably will be below 0 since we're going to be dealing with low numbers. So it's a good idea to put 0 in here. I chose not to, just so I could make that point for you. None of the things that I do today, because I'm not using a normal distribution, none of the distributions that I use, I'm going to use a log normal, and I'm going to mention a gamma, and I'm going to mention a Weibull distribution. None of those go down below 0. And non-parametric methods just care about ordering, so they don't care. So there's no need for a 0 here unless you're doing a normal distribution. So the less than 0.05 is from NA to 0.05. The detected 25 is from 25 to 25, and the greater than 30s are 30 to NA at the upper end. So I've named them the low and the high columns for thiomethoxam. You can do QQ plots to look at the distributional shape. This is a normal distribution represented by the blue line, and these data don't fit it very well. And so we would not use a normal distribution. This is the QQ plot for a log normal distribution represented by the blue line. These plots come from one of the webinars that's up on our training site called Fitting Distributions to Data with Non-Detects. So here, it only had non-detects at the low end, and so it had the first certain percent. I forget what that percent was now. And then all the detects are up here, and you can see it matches pretty well the blue line. So this is going to be something that looks a lot like a log normal distribution. All that I've done is change these last two dots to be greater than 30s. So you would not see them on the plot in this case. Non-detects or greater thans do not show on these QQ plots, but their percentages are represented on here. As whatever percent was below this one low detection limit, let's say that's 15% of the data, then the first 15%, it's just blank here, but the first point that's detected is up around the 16th or 17th or 18th or 20th percentile, whatever it is. So here's another look at the same data, and we've got this curve. The curve represents a log normal distribution. So I've just stepped into the world of parametric methods. By maximum likelihood, you fit this curve. What does that do mathematically? It tries to fit the curve to the top of the boxes of this histogram, if you want to think of it that way. So those are the detected data in the gray bars, as well as the percentage of data that are below, so in this case, left of the detection limit. And here I've just set a detection limit at 2, I believe. And so there were 14% of the data below 2. When it fits this curve, it tries to fit both the curve to the bars and the area to be 14%, and it gets to where the best fit is at 12%. So if it went closer to 14, it would not make the fit with the bars apparently quite as good. And that's probably because of this up here. I made 2 of the data points greater than 30s. There's about 200 data points, so that's about 1%. So there's 1% of the data above 30, and it wants to fit that in here at 1%. And if it pulled this back to make that 14%, it would not have the 1%. So it's mathematically giving you the best fit. And when you say this is a log normal, which is what I did, it determines the shape here that looks like a hydrograph. So that's how maximum likelihood works internally. It's going to fit the curve to the data, and then the results that you get back are using that curve. So here is one way of looking at data. This is a group test, a parametric group test. So it's a censored version of what you would be familiar with called analysis of variance. And I've assumed a log normal distribution. The command up here says dist equals log normal, because that's what fit the data well. And so when I assume a log normal, it's saying that the logs of these data, I'm testing those to see if they are different in the 4 groups. This is the output, this is the table. It looks a lot like a regression type table. That's because the command is called servreg, and reg stands for regression. So we're actually doing regression to get an ANOVA type of procedure. The Y variable is represented by this entire thing from serve, capital S serve, all the way down to interval 2 quote, end quote, and parenthesis. That is the Y variable. So what is that? It's saying that my Y variable has 2 columns, the low column and the high column, and the type of data I've just given to you is interval 2. So it knows that that's the low and that's the high. So that's the Y variable. Then there's this tilde, which means in most statistics packages, the tilde represents modeled by or explained by. And then this is the X variable, if you want to think of it that way, and would be the X variable in regression. And so here it is too. It's the grouping variable called sampling event. And sampling event had in it 4 text pieces of text. One was 1 dot pre-plant, then 2 dot post-plant, 3 corn tassel, and 4 goldenrod. So those are just letters in the data set in that column. That character variable is defining 4 groups. So what is this output? Here's the intercept. The intercept is going to be the mean, and in this case, the mean logarithm for the group that's not shown. That's kind of the base group, which is 1.preplant. And unless you tell it otherwise, that base group that it chooses is just going to be the first one in alphabetical order. That's pretty standard in software because it doesn't know what ordering you want. You can change that, but that's the default. So the mean log for that preplant group is a minus 0.549. And so if you exponentiate that, you get the geometric mean, not the mean, but the geometric mean back in the original units of 0.577. So that's the summary statistic you have here. That's what's being tested, of the difference in the geometric means among these four groups. The second group, post-plant, has a value here also. And this value is the difference between the mean log for the first group and the mean log for this group. So this group is 0.2, the post-plant group is 0.2234 lower in log units than the one group, the pre-plant. So it's going to have a mean logarithm of minus 0.55 to round, minus 0.22 is minus 0.77. And so it's going to have a geometric mean of 0.46 back in the original concentration units. And similarly for corn tassel and goldenrod has these differences from the first group, 0.549 minus 3.3699. And so you can turn those into geometric means. So all of this can be done in R. I'm working on a little bit more user-friendly output for people that are not used to doing this. This command, servreg, is in the survival package. So these MLE parametric methods are all in the survival package for R. Here is the test down here, has a chi-squared test statistic. The p-value is what you should be familiar with. If this is less than 0.05, and this is way less than 0.05, then these groups are different. These group geometric means are different. These group mean logs are different. Yes, you could do this, assuming a normal distribution to test for differences in means. You'd say dist equals Gaussian up here. The default in servreg and any other survival package is the Weibull distribution, another skewed distribution like the log normal. And that's because in survival analysis, they don't think that anything is close to a normal distribution because it's always skewed, just like our data are always skewed. And they don't really pay much attention to means. So they deal with medians and other percentiles. You could do that. This test, because it's a parametric test, would be affected by that non-normality we saw in the QQ plot, and the p-values might be too high. All right, so this is the output for doing group tests. Here's how you would do regression itself. I've changed, this is basically all the same thing. I've defined the y variable here and called it serve.thia. And then I can just use that here. So it makes this one, instead of one long command, it's just separated into two, that's all. Serve.thia tilde, and then the sampling time, that's the variable I made up. That was just 1, 2, 3, and 4. Again, telling it dist equals log normal. So we're going to see if the logs of the thiomethoxam concentrations are decreasing in the order of 1, 2, 3, 4. And again, a more realistic example, but I didn't have that data. Or if it's up there on the Ontario site, then I didn't go back and get it, just to be honest, is time would be a good example of doing this as a trend test. And so this is doing regression here because the X variable is continuous, it's not categories, it's not text. And so sampling time here, this is our regression slope, minus 1.67. That's telling you it's going down over time or over the sequence 1, 2, 3, 4, and we saw that in the box plots. Here's the p-value for whether that slope is 0 or not. It's very small, and so it is not a 0 slope. It's much more significant. So we would use this as a model if it made sense with this X variable. So that would be our regression. It would be the intercept minus 1.67 times the sampling time for a prediction of the log of the thiamethoxam concentrations. So for parametric methods, just as a summary, you must assume a distribution. No substitution is done on any of these things, anything that I'm going to talk about today. The information in non-detects is in the proportion of the data that are below each threshold or above the high threshold. So there's no numbers stuck in for any non-detects or any greater thans. And there's a whole literature in the survival analysis on the greater than values that have shown over the years, long before we paid any attention to it, that sticking in a number for those high greater than 30s is a terrible method. And we've seen the same thing in our discipline in the sticking in numbers like a half the detection limit. So that's accepted, and none of these procedures use that at all. Okay. So the non-detects affect the computations of a mean, a standard deviation, and percentiles through their observed percentage of values below and for greater thans above each threshold. Typically, gamma, Weibull, and log normal, which are all skewed distributions that do not go below 0, are used in the software, with the Weibull being the most commonly used one because that's what they use primarily in survival analysis and medical statistics. And so they should be the models that we choose as well. Greater thans are just a mathematical reflection of what's been done by folks in the environmental fields in the low end, taking the proportion less than a detection limit and saying, well, I can do the same thing on the upper end. Actually, they did it first in medical statistics. So looking at the proportion of data above that high threshold of 30. And it requires, to do that, interval censoring. That's the format you need in order to represent both of them in a data set. So you will be using this interval 2 type or format when you put in your data. All right, moving to non-parametric estimates. It's similar to computing just sample percentiles of the data and the tests, like the Kruskal-Wallis test or the Wilcoxon-Rank sum test. Those are all just dealing with percentiles anyway. So there is a procedure called the Kaplan-Meier percentiles that when you were just dealing with values on one side, just for us, just the non-detects, it's called Kaplan-Meier. A statistician named Turnbull came along a year or two later and said, hey, we can do this on both sides. And so gave a interval censored version of the Kaplan-Meier procedure. And so those are that's called the Turnbull estimator, but it would allow you to put in interval data and estimate still a cumulative distribution function, or CDF, and that is just the set of percentiles for the data. It's done with a command called survfit in R, part of the survival package, but it's doing non-parametric procedures. And the scripts that will come out soon, and I'll tell you first, I'm going to put them in a second NADA, non-detects and data analysis course up on our training page. But I am in the process of negotiation to see if we can get all of these things into the NADA package of R. So I would expect the course to be up in June, and sometimes later in the year, probably more like the last quarter of the year, it may be out. Hopefully it will, and all the indication is good that it will be out in the NADA package. And so these things would allow both left and right censoring, and you could do things like computing a mean with those. And so I'll give you an example of that in a minute. All right, the way these methods work, and all these overheads come from overheads. That's showing my age. All of these slides, all of these PowerPoint images are from another webinar. So if you haven't seen it, it's on the webinar on the mystery of non-detects, how censored data methods work. So this is showing you the Kaplan-Meier procedure, which is very much like the Turnbull. And so this is a data set, these numbers here on the left that do not have any non-detects. And so you can graph them just as a bar chart with the values for that y variable down here. And each one has a height, each bar has a height of 1 over n, 1 over the number of data, or 1/10, 0.1. And so if you color in this area and compute the total area here from the CDF, which is the blue step function, that CDF down to 0, that's the mean. So if you sum up all of these areas, you're taking the value for the value of y. In this case, it's 0.38. The next one is 0.77, then 0.81. These are the same numbers as over here on the left. And the vertical distance is 0.1 in every case. So it turns out to be just same as summing up all of the data and dividing by n, which is what the mean is. So that's a value of 1.355 for this data set. That's not the same as the Ontario data set. So what Kaplan-Meier does is to reassign the probabilities when you have non-detect. So there's no probability assigned to a non-detect because you don't have a value for it. A less than 5 is not 5. So what it does is it takes the probability, that 1 over 10 in the previous slide, and pushes it down to the other data that are below it. And what that does is saying that my best guess at what the shape of the data is below 5, let's say if I had some less than 5s, is the observed data below 5, rather than a smooth curve theoretical distribution. I don't want to assume one of those because I'm a non-parametric procedure. So I'm going to use the data to best represent the shape of the data that I've already seen. And so that same process works on the upper end as well. So with the example of doing it on the lower end, if I change the 0.91 in this data set to less than 1, and so its 0.10 no longer exists for the 0.91, what happens is that less than 1 changes the probabilities associated with the percentiles for these lower observations. So what it does is take this 0.1, splits it up into 4 pieces because there's 4 observations below. And so the detected 0.91 now has a probability, a height of 0.125. So it's giving more weight to that and to this detected and this detected. And then the bottom one I set to be less than 0.5 to show you that in Kaplan-Meier, and this would be true on the upper end as well, if you don't have anything below it, then it just uses the only number it has, which is the detection limit. That's the standard procedure in survival analysis. So if you only had one detection limit, this Kaplan-Meier procedure is essentially the same as substituting in the detection limit itself. So that's the way it is. And it's of most use then when you have multiple detection limits, in my opinion. All right, so each of those bars has a height of 0.125 now, and then that area, you can see the old uncensored blue here is the CDF for the original data without non-detects. And it was 1.35, I believe, before. Now it's 1.33. That's the best estimate. That's the Kaplan-Meier estimate of the mean. So that's kind of underneath all of these types of procedures. Here's the serve fit command with the y variable by sampling event. So that's just printing out the median, a confidence interval, 95% two-sided confidence interval on the median. It's a little bit more involved with this command to get out the mean. So I'm done that with at least the first version of a script that will compute the mean. So that's this thing, our mean interval 2 down here. And here I haven't yet written it to split it out by groups when there's groups, so I have to just put in for one group. So where the sampling event is equal to the first group, and it's censoring indicator. So this is with a indicator rather than a column, 2 columns, low and high. So that's going to get changed as well. And it gives you back the estimate of the mean for the first group. And that's summing up areas under Kaplan-Meier. So this has nothing to do with a normal distribution, but it still gives you an estimate of the mean. So this would be the mean thiomethoxam for the first group, the pre-plant group. So then you can do testing as well as estimating summary statistics without assuming a distribution. They're similar, tests are similar to the rank sum test and the Kruskal-Wallis tests, depending on how many groups you have. They're built on something called scores, which are just basically percentiles done by either Kaplan-Meier or the Turnbull process. And it's generally called the Pareto test. That's the test name for what's in R. There are slight variations because they're using slightly different scores, slightly different functions of these percentiles, basically as the ranks that are used, if you want to think of them that way, in the tests. And so these similar tests go by different names because Prentice came along and modified the Pareto test. HF1 stands for the names of two other statisticians, Harrington and Fleming, if I remember right. Generalized Wilcoxon usually means I didn't bother to figure out which of these type tests I did, so I'm just calling it generalized Wilcoxon test. I think often it's this last one, the Gahan test, which is again the name of the person that developed it. And they're all mathematically very, very similar to the Pareto test. So I've just used what's in R. And these tests are these are the non-parametric tests. They're in the interval package of R. So you can go find them. I'm going to be writing some scripts. Here's one that's just about done. ISEN one way is to do a one-way Kruskal-Wallis, like a one-way analysis of variance, but a non-parametric test. And if you've seen some of our other videos, other lectures, you've seen the SEN one-way command is doing this for just with non-detects, the I in front saying that I'm going to get the input so that it looks like you can use greater thans as well as less thans, or you could put in the below the method detection limits and then in between detection limit and quantitation limit kind of structure as well in this ISEN one-way command. All right, this is just the review of the picture of the box plot showing you that it goes down 1, 2, 3, and 4. You should see some difference in the groups. It's a pretty strong difference. So let's do them. Here's the ISEN one-way command. This is underneath using commands in the interval package. But what I've done is made the output, more easy to understand. And I've added in a sequence of multiple comparison tests. If you don't know what multiple comparison tests, a previous webinar talked about those, and it's up on the training page, and you can go for free and take a look at it, how multiple comparison tests work. So I think the name of it is which things, the video is which of these things is not like the others. So that was from last year as well. So there's a lot of things up on that training page that you can view without paying any money, and some things that have a lot more detail in the courses if you do want to purchase those. Okay, so we have here the overall test. Is there any difference in the groups? The p-value is really, really small. So yes, there are differences among these groups. You can think of these as a test for difference in medians, although it's more technically a test for differences in the CDFs in this whole set of percentiles. And that's true also for Kruskal-Wallis. So it's the same kind of test. And when you look at these multiple comparison tests, they are all different from one another except for groups 1 and 2. So if you put the A, B, C, the lettering kind of convention down here, it would be that pre is the same as post. It's not significantly different than post. But then each of those is different than the corn tassel, and each of those is different than goldenrod, and corn tassel is different than goldenrod. So going back here, it doesn't distinguish between these two, pre-plant and post-plant, but it does distinguish any of these with all of the others. So that's the ISEN one-way script, which will be in a course by June and will hopefully be in the not a package later in the year. Let's see. This is a command in the interval package itself, so I haven't made this friendly or not, and so I'm going to show you the output that is not as friendly as so what you get with the IC test here. Again, it's just the y variable tilde the x variable, which is time now. So this is doing not really regression, but really more correlation. It's not giving you a formula for it, but it's going to give you a measure of, are these two things related? Do they go in anything other than a random relationship? Does the thiomethoxam concentrations, do they go down over time or up over time? Again, given that time isn't really time, it's the numbers 1, 2, 3, 4, but I made it up. So this IC test is in the interval package. This y variable is up here, that serve command. We did this before, so I'm just reusing that, showing it here to you. Gives you back a log rank trend test if that were time. And if it's some other continuous variable, it's a trend in whatever that variable is. So it's looking at a correlation between y and x. It's using something called a log rank statistics. That's one of the things I'm investigating. I think there are ones that are more similar to something like Kendall's tau. But for what you get a p-value that says it's really small. This is not just random. The direction of y is related to the direction in x. Gives you a score statistic, which is not a correlation coefficient, but it does show direction, at least in the direction, not surprisingly, is backwards from what we might think. So here's the text that comes back out. This is fine, and it's very standard for people that are only dealing with greater thans, because that's what they deal with largely in medical statistics. It says this score statistic is positive. That means larger covariate values give earlier failures than expected. So what does that mean? Covariate values, just the x variable. It's the covariate, the covariable with the y variable, which is the variable you're interested in. So larger sampling times give earlier failures. That means smaller detected values. Our detect are the survival analysis failures. A failure is something that you have an exact value for. It's not a censored value. So what it's saying is that a larger x value gives a smaller y value. So we've got a negative correlation, which is what it looks like in those box plots. The concentrations are going down as the numbers 1, 2, 3, 4 increase. So these non-parametric methods exist for interval censored data, which handle greater thans, or they handle the data in between detection limits and quantitation limits. They use the information in the detected values plus the percent of data below or above each limit to compute these statistics and hypothesis tests. They do that without substituting numbers for any of them. The input format you have to give is an interval endpoints format. The parametric methods are in the survival package. The non-parametric methods are in the interval package. So you can go and look at those if you're familiar with R and make use of them right now. Or starting in June, there'll be some friendlier things that you can use. You can find this stuff not just in R, but in SAS and in Stata. Those are big name statistics packages. Stata is probably the primary one for medical statistics. Other statistics software is less likely to have this interval censored formatting. Minitab does for some things, but not all of what I want to do. So you might find them. You could check the survival analysis procedures in the package that you have and see if they have interval formatting. If you want more information on interval censoring, it's in the book. There's a picture and the name. So thank you for attending. And I'll look at the questions here. So let me jump to those. You can keep typing them in if you haven't typed them in by now. Andre says, says, can you describe an R package we could use to do multiple comparisons following a significant test result using a Kruskal-Wallis test? Sure. If you went to one of our previous webinars on multiple comparisons, you'll see a script that does just that. And in that webinar, which is up on our training page, is the one about multiple comparison tests. Then you'll see which I went ahead and, like I did today, put in the R
commands
that do that. In R, there are, if you know where the information about packages is in the CRAN site, the main R site, there are task views, T-A-S-K views, which there's one for survival analysis. And what those task views are, they tell you, here's things you might like to do, and here are all the packages that do them. And so you can read those task views and find out about packages you don't know of. And then finally, there is a pairwise.wilcox.test command that's in the base package of R that does multiple comparisons following a Kruskal-Wallis test. It's just a whole series of rank sum tests, which is what you should do anyway. So while you can go and do that in a separate package in the serve minor or whatever it is that the package is, you can just do that with the command pairwise.wilcox.test. And all of that information about the pairwise.wilcox test and other pairwise procedures is in our new version of the statistical methods in water resources, which the second edition is just on the verge of being out, and now everybody's doing work from home, and so I don't know when it's going to be out. It'll be out soon. They were saying the first week in April or so, and so I don't know what it's going to be now. But those pairwise procedures are in there. So I don't see any other questions. So with that, I will close it up, and thank you for attending. Thank you and goodbye.